All right, good morning. Welcome to day one of reInvent. If you don't have your headphones on, stick them on. If you want to listen to us, keep them on pink. If you want to listen to somebody else, put them on a different color, that's okay. But we can tell. So event-driven architectures are all the rage in cloud-native development, right? We hear about EDA all the time. And a very simple definition of EDA, data changed, something happens, we want to respond, right? The canonical example of that is e-commerce, right? We're using events as kind of the connective tissue to choreograph a flow between ordering and fulfillment and shipping. These are always like system-to-system type interactions. But there's always, almost always, some human element that those systems tend to ignore. There's somebody like me sitting there obsessively refreshing to see where my package is or when my pizza is going to be delivered, right? And I can be a little obsessive about it. So in our session today, we're going to explore some technical patterns and the trade-offs to implement seamless front-end experiences. We're mostly going to focus on the cloud side of things, if you will, but we've designed this talk for front-end engineers, back-end engineers, full-stack engineers, and the mythical 10x engineers out there. Okay? We're going to talk about some front-end, we're going to talk about some back-end, because this is really about the marriage between the two. So you can create very rich, interactive, event-driven front ends. And our goal is that you can leave with a pretty good understanding of those architectures and the trade-offs so that you could go implement something today or even during the session if you're feeling ambitious. My name is Josh Kahn. I'm the worldwide tech leader for serverless here at AWS. And joining us in a little bit is Kim Wendt, who is a senior solutions architect from AWS. So we see these types of interfaces all the time. This is my quick mock-up of my flight here to Vegas yesterday, right? It's got some information about the flight. It's got a little bit of now boarding type information, kind of an update about what's going on with this particular flight. But you can imagine something like this for stock quotes, sports scores, even, again, the current location of a delivery. But we see these types of things all the time, not just in the mobile apps, right? We see these types of interfaces all over the place, airports and train stations. This is actually from a flight I took recently that went through Frankfurt, and there's just a lot of data here. And we're going to come back to this a couple of times, but there's lots of data that we might load first up front, and then we want to update things individually in little pieces as we go. And we're going to explore patterns on how to do that. But we're also starting to see things like this at your local fast food restaurant, at coffee shops, and other places. And if you happen to have been to the certification lounge already, or you're planning to go to the expo when it opens later today or sometime through the week, you can actually experience event-driven coffee at our serverless espresso booth. So here, there's actually two different messaging patterns in action. On your right is kind of the big screen behind the baristas. And it has an overview of all of the coffees that are in the queue to be made, right? It's very much a broadcast message. We're going to come back to that in a minute. And then on the left is the details of your order that shows up on the mobile device that you place the order on. And it's more of a point-to-point message, right, that talks about here's the status of your particular order. And when I've worked at serverless espresso before, I get a lot of questions from people like, how did you build the interface, right? How did you make it update? Because it's actually kind of hard. And that's one of the things that inspired us to create this talk. The other is that user interfaces, just by their nature, are event-driven, right? When I click on a button or when I scroll or even linger in one place for too long, it's an event, right? And maybe it's an event that a marketer cares about, but it's an event that some event handler is going to try to pick up. So if we click on a button, in this case, we're just going to pop up an alert, right? You clicked me. And we're just writing some really simple code. This is an example in React, but there's lots of versions of this. There's an event, something happens, and we want to do something about it. Sounds really familiar, right? Kind of like my simplified definition of EDA earlier. But we can do more. We can also load some data. right? In this case, we're going to load the data when the button is clicked, use the reactivity of the UI framework to go update some elements on the page. But this is very synchronous in this case. We're waiting for the data from the API to load. We're going to update the element on the page, and then it's static. There's really no mechanism in this very simple case to update things. But we all know the world is asynchronous, right? Things are happening around us. The package is getting closer to my house. The flight might have landed and is taxiing up to the gate now. Things change all the time. So we wanted to explore ways that you could build more interactive and up-to-date interfaces using a bunch of different AWS services. Because frankly, and you've probably experienced this, real-time data tends to make things better, right? It's more up-to-date. It's a better user experience overall. Because updates to like my flight status are kind of important. If I go to the wrong gate, probably a bad move, particularly if I have to run across the entire airport to get to the right place. Anybody ever have that happen? Because I have. But if you've ever tried to build this type of experience, it's challenging. There's a different set of technologies involved. There's different teams involved oftentimes. But the most straightforward approach that we see from customers is to utilize a technique called polling. Right? So polling involves the front end calling the back end on some regular interval, some regular basis, and asking for updates. If you're a parent like me, this is the equivalent of your kids sitting in the back seat on a long road trip asking, "Are we there yet? Are we there yet?" Every couple of seconds, essentially, right? So polling can be expensive. In this case, there's some hidden costs. In the parental case, it's really just frustration and annoyance. And you can probably work through that. So in this case, we're getting the full response back oftentimes. It's not as timely, right? The event is happening somewhere else, but we don't actually see it realized on the interface until the client decides to poll again. Don't get me wrong, polling makes a lot of sense in some cases. Sometimes the data is changing really rapidly, and sometimes we don't need to know about every single item that gets updated. If we're running a very fast-growing food delivery service, I don't need to update some dashboard with the total number of orders that day every time one comes in. I can just update it every 5 to 10 minutes, right? So polling, how do we implement something like this on AWS? Well, we've got EventBridge, our event bus, and this thing is going to be kind of spitting out events. You'll see this over and over again as we go. We have a Lambda function that we're going to call an event handler. That function takes the event published by EventBridge or on EventBridge. It pulls out the data it wants, writes it to a DynamoDB table that we're going to call a view model table. And then it kind of stops from a processing standpoint. When the client asks for data, it's going to go through something like API Gateway. API Gateway will invoke another function, and it will go get the data it needs to fulfill that request. Pretty straightforward. And this is fairly familiar to most people. It uses REST semantics. It doesn't require anything like a WebSocket to make it work. It just kind of works. But there are some hidden costs here. First, again, this can be a little bit slower from a user experience standpoint. It's only going to update on the polling interval. It's also a little wasteful and chatty, right? There's a lot of extraneous network calls. Unless you've built the API specifically to kind of handle, just tell me what changed, you're going to be sending data across that the client may not need. It's also going to put more burden on the server because you've got all these network calls that may not be necessary. Now, in the serverless world, we just add more Lambda functions until you hit some limit, right? But you're still putting added pressure on the back end. The trickiest hidden thing here, though, is that the client now becomes responsible for calculating the delta between the current request and the previous request. And sometimes with complex data, that can get a little bit cumbersome and hard and error-prone. And if you've ever built client apps, they also can be a little bit harder to update at times, right? We've got to push an update maybe through an app store. So you don't want to make too many changes if you can help it. So there are practices we can use to help improve polling, but our opinion is that there's asynchronous approaches that address a lot of these challenges. And generally, we're going to call these a subscription-based approach. The client asks the server, hey, let me know when something changes. And just tell me about that. This is the equivalent of me turning around and saying to the kids, I'll let you know when we get there. Okay, just leave me alone the rest of the ride. This generally works best for small changes, not bulk updates, and you'll see that as we go. So we synchronously bulk load, a lot of the data for that airport departure screen, and then just use a subscription-based pattern to update individual flights as the data changes. Now, we're primarily going to be using WebSockets for subscriptions today. You might also be aware of an approach known as webhooks to update subscribers. Also works, not as applicable for the types of clients that we're talking about, web, mobile interfaces. All right, a couple things before we get into the technical weeds. Broadcast and point-to-point messaging patterns, I already mentioned these. So broadcast messages going out to a large number of subscribers. What's the weather like in Las Vegas? Tell me about all the flights leaving Chicago. Point-to-point messages are going to a particular consumer, maybe just one person or a small number. Right? This might be updates on an individual flight, or maybe where my package is individually. And choosing between broadcast and point-to-point how to implement broadcast and point-to-point actually differs between the architectures that we're going to look at in a little bit. So depending on your use case and what you're doing, that may lead you down one path or another. Some are really good at both. Some are only good at one, but not the other. Really high-level architecture, just to keep in the back of your mind. I apologize to anyone in the airline industry today. This is a gross simplification of what's going on. But we have a bunch of events coming from different services. They hit an event bus, and then we're going to implement what we're calling a backend for front-end service. So we're going to implement various flavors of this backend for front-end, or BFF. That's a common architectural pattern that tightly couples the needs of your front-end application, web, mobile, whatever, with some optimized back-end API. And our goal is to handle the orchestration, persistence, and aggregation of data that's needed by each front end. And you might have a BFF for your iOS app, for your Android app, for your web app. On and on we can go if we'd like to. And normally in distributed systems, we think of coupling as kind of a yucky word, right? Like, we don't want coupling. But in this case, people tend to find this is useful, right? So we give teams more autonomy to have better separation of concerns and more flexibility to decouple other aspects of the overall system. So our patterns and the sample code that we're going to share with you at the end, we built this whole thing out. Kim's going to show it to you. It really only focuses on updating the client. There's a lot of other things that you could do if you wanted to fork the repo and implement other bits. We're only interested in updating the flight status. Also, we realized that there's a lot of redundancy in what we were building and what we were showing you. So being good architects, we didn't want to repeat ourselves too much. So you're going to see a common pattern through almost all of the architectures that Kim's going to run through. We're going to call them the event processor right on the screen. But what's happening there is we've got event bridge, the event bus. There is some event bridge rule, right, where we've defined some filters only to listen for the types of events we want. Departure delays, boarding, etc. There's a Lambda function called an event handler. It again picks up that event, decides what to do with it, writes it to a DynamoDB view model table, and then we're going to use a DynamoDB stream to stream those changes out to the rest of the system. And the rest of it we're going to call the stream handler, and that's where all of these different options are going to come into play. Quick note on when you look at the sample code, it's not a DynamoDB stream, it's actually a Kinesis data stream. The reason we did that was so that we could have more than a couple of consumers feeding off of the same stream. Functionally, it's pretty much the same. All right, so we're going to be looking at 3 different interaction patterns through the rest of the talk. Kim's going to spend the bulk of our time today talking about real-time events. We've already shared a few examples of those. I'm going to come back towards the end and talk about long-running processes. These have really kind of become more common for us to be talking about as people talk about generative AI more, right? Because they can take longer than 30 seconds to respond. And then the last thing we'll briefly mention is push events. Push events functionally feel a lot like these real-time event patterns, but there's some other players involved and there's some different semantics. So with that, I am going to hand it over to Kim.
Thanks so much, Josh. Really appreciate that introduction, kind of level setting us on what we're about to talk through. So for each of these patterns, I think we're going to run through 5.5 or so. I'm going to talk to you about the pattern, how it integrates into the stream handler that Josh just talked about, which aggregates all of our data into our model view table. And then we'll kind of summarize what the trade-offs are with each pattern. Because as we know, everything that we build has trade-offs. So the first pattern that we're going to talk about is what we're calling the two-way WebSocket pattern. And this pattern is powered by Amazon API Gateway WebSocket APIs. And if you're not familiar, these are managed WebSocket APIs that are what we call full duplex. So they're bidirectional. Clients can interface and send information back to the server. Server can send information back to the clients. Before we talk about how this hooks into that event processing workflow, there's actually a bit that needs to happen in order to know which clients we're going to send updates out to. So if we start on the left-hand side of our screen here, WebSocket APIs and API Gateway have special connect and disconnect routes. When a client connects to your API, they're actually hitting that connect route. We're doing some special processing to assign a unique connection ID to that specific client and persist that in what we're calling the DynamoDB clients table down there at the bottom. Similarly, when they disconnect, they hit a special disconnect route. We remove that unique connection ID from that clients table. You might already be starting to see in this pattern that connection management is a bit do-it-yourself, right? We're tracking clients as they're connecting and as they're disconnecting. The way that ties into our event processing workflow is once events are coming through our system, our stream handler is processing those events, might be doing some filtering, but it's also checking our clients table to see which clients are actually interested in these updates. So the stream handler has to essentially do a lookup to get the connection IDs for clients that actually need that update. And then for each individual client that's connected, the stream handler performs what's called a post-to-connection API call. And it does this for every client that's connected to send them the update. So you might also be starting to see that there's no real way to do a message broadcast, to send one message out to all of your connected clients. Again, this is a bit do-it-yourself. You effectively have to iterate through all of the clients that need that information in your stream handler to get those notifications sent out for the updates. So we kind of summarized a few of the trade-offs so far. Connection management is do-it-yourself. Message fan-out is handled by you in the stream handler. So what you eventually end up selecting as your compute for the stream handler becomes really important. You know, Lambda has its limits, and if you're connecting, you have multiple, like millions of connected clients, iterating through that many clients, might reach those limits from a Lambda perspective. On the positive side, though, this is a really flexible solution, right? This is just vanilla WebSockets under the hood. You get the full bidirectional communication, so it might be a really good fit for chat applications if you're building those. Additionally, on the trade-off side, because this is just a WebSocket API, what Josh mentioned before about doing a query up front to essentially get all of the information back before you start retrieving those real-time updates would need to be done via a separate API endpoint. For that, you could potentially use a REST or an HTTP endpoint powered by Amazon API Gateway, but it would be a separate API endpoint compared to the WebSocket API that you're using for your real-time updates. For each of these patterns, we're also going to talk about what authorization modes are supported because security is job zero at AWS. For API Gateway, WebSocket APIs, we support IAM and Amazon Cognito identity authorization, Lambda for any type of custom auth that you need. And what's unique to this pattern across all of the patterns that we're going to talk about today is we actually support public WebSockets. I will actually show that in the demo as well. This is the only pattern that has that kind of true public API option available. All right, our next pattern we're going to talk about involves AWS Appsync, which is my favorite service personally. And in this pattern, AWS Appsync is, again, acting as the front door for us. And if you're not familiar, Appsync is a fully managed GraphQL and WebSocket API service. And if you're not familiar with GraphQL, GraphQL is a query definition language, which enables you to define query operations for reading data from your API, mutating or modifying data, and then the real-time capability that it provides is powered through subscriptions. And in Appsync, subscriptions are triggered as a result of a data mutation. So mutation happens, subscription gets sent out to any subscribed clients to let them know that the mutation actually occurred. And that's really important here, because if we talk through how this interacts with the event processing workflow, Josh talked about before that we're actually updating our data earlier on in that event processing workflow, right? We update our view model table in DynamoDB, and then we consume the changes that are happening through DynamoDB streams. So our data has already been mutated by the time we hit that stream handler function. And so the way that we kind of work around this to trigger a mutation without actually modifying the data, because it's already been modified, is we use something specific to Appsync called a none data source. And you can think of a none data source as essentially a pass-through. Input comes in, it does a faux mutation, doesn't actually change any data, but it is able to then trigger the subscription out to our connected clients. What's really beneficial about this solution compared to solution one is that Appsync handles connection management for you. So we no longer have to worry about our clients coming in, having to track their connection IDs in a DynamoDB table, and then iterating through to send them out the updates. Broadcasting is built into Appsync, and we'll kind of show how that works in a little bit. So to add a little bit onto some of the trade-offs with this approach, talking about benefits here, this is a really extensible approach. In our event processing workflow, we've been talking about DynamoDB and using the change data capture feature through DynamoDB streams, but you could just as easily plug in Amazon Neptune, for example, which is our managed graph database, which also has a streams capability, and plug that in exactly into this architecture as it is now, and still enable the same subscription capabilities out to your connected clients, which also enables you to filter the stream as needed in that stream handler function. Because this is using AWS Appsync, there is a bit of a learning curve in the GraphQL side of things. GraphQL is a new language and sometimes can be a barrier to teams adopting it because it doesn't have the familiar REST semantics that we're already used to through traditional APIs. But my opinion, the benefits of leveraging GraphQL generally outweigh the trade-offs that you're making, with one of them being that you can use this API for queries, mutations, and your real-time updates. So all of that is included in that singular API endpoint. From an authorization standpoint, Appsync is pretty flexible. It supports IAM, Cognito, Lambda for custom authorization, and one that's unique to Appsync, which is direct integration with OpenID Connect. So you can actually provide the API with your issuer URL, and when you pass it a token, it will actually go off and validate that token for you, so you don't have to write custom code. All right, we're sticking with Appsync for this next pattern, just because I love it so much. But this pattern is what we're calling the direct to GraphQL pattern. And essentially for this pattern, we're leveraging a direct integration between Amazon EventBridge and AWS Appsync mutations. So we don't have the event processing step here anymore. We don't have a stream handler step anymore. And so we're essentially using a mapping between the event coming from Amazon EventBridge and our mutation, right, our data modification function in Appsync to trigger the connection between the two. Because of that, because we're not using the event processing flow anymore, we need to shift our view model table from DynamoDB, which was further upstream, and we can actually use that direct integration between Appsync and DynamoDB to persist our data directly from Appsync. We do this in Appsync using something called a resolver, and a data source. And so we're directly connected. That resolver can be written in TypeScript, JavaScript, or if you're feeling like doing it, Apache Velocity Template Language. And then you essentially write a bit of code to persist those events to your data source. There's a couple things to call out here in terms of trade-offs. Because we're using a direct integration, this is pretty simple to implement, right? It's a direct integration between the two. We have a lot less moving parts, right? We don't have a bunch of Lambda functions that are doing the filtering for us. We don't have to use DynamoDB streams to get those updates. We're also able to do our data mutation and our update out to subscribers in a single step, right? Before, in the previous pattern, we were using our none data source to kind of trigger that faux mutation to get the subscription out, but here all of that's done in just one single step. Similar to the previous pattern, we have a lot of flexibility in this, sending updates out to our subscribers. And with this approach, we also have the ability to support private connectivity. That was true for the other pattern with Appsync as well. We can use private APIs with AWS Appsync to restrict communication just to our VPC, if that makes sense for your workflow. Again, this is using GraphQL. These are still one-way subscriptions. And although I said it is really simple to get that connection working between Amazon EventBridge and Appsync, there are some tripping hazards that you could potentially run into, which we'll talk about. And we have some solutions for you because building the demo, we did run into those. So we'll talk you through how to avoid those. But let's talk a little bit about broadcast and point-to-point to show you how this is very easy to do within Appsync. I mentioned before that this is all handled for you. You don't have to worry about building out any custom iterators to send updates out to clients. And it really is just as simple as defining this as part of your schema and then implementing it on the client side. So it's a bit of both in this architecture. So if we start on the right-hand side, this is a snippet of a GraphQL schema. What we're showing here essentially are two mutations. Again, mutations are data modification operations. We have one for creating a flight, one for updating a flight. And then on the bottom, we have our subscription type. And this subscription type is tied to both of those mutations via that AWS _ subscribe directive. And that allows us to essentially make that connection and marry up our mutations to our subscription operations. The important thing to call out, though, for broadcast and point-to-point is that optional flight ID parameter for our subscription. So when that flight ID parameter is specified from the client side, that's essentially saying from the client, hey, I only want to get updates for this one flight ID. If you don't provide that flight ID in the subscription, the client's essentially saying, hey, I want updates for every single flight. And that really is the difference between broadcast and point-to-point with AWS Appsync. It's a bit of client, a bit of server. Appsync is really smart. It handles all of that for you on the back end as long as you provide the parameter in to do that filtering when you establish the subscription. From a code implementation standpoint, again, this is really easy just by passing the variables if you're doing a point-to-point subscription, or if you're doing a broadcast, you don't pass any variables and you just get all the updates for every single flight ID that you want. This is using the AWS Amplify API client library, which is very useful for implementing code for AWS Appsync as well as other services. But these are just WebSockets under the hood, so you could use something like Apollo if you're familiar with that library, or any other GraphQL library to interface with those WebSockets. I mentioned before that there are some tripping hazards with this approach, and so I'll say a brief word on mutation selection sets. And if you're not familiar, selection sets are specific to GraphQL, and these are essentially what gives GraphQL its power, because it lets the client decide what information it wants back from the request that it's making. So I go ahead and make a mutation. I specify all the fields that I actually want back as part of that request, and that's what makes up the selection set. So on the right-hand side, we have a create flight mutation, and that chunk at the bottom where I'm essentially listing out all of the parameters that I want back, that's what the selection set is. The reason why this is so important in our EventBridge and Appsync direct integration is because if we leave out something like the flight ID, but our subscribers are expecting to get that back, what they're actually going to see is a null value being returned. because on our mutation, we didn't provide that information to them. So they won't be able to get that on the subscription side. And this, again, matters when we're doing that filtering based on point-to-point and broadcast. So general rule of thumb, if you're using this integration or if you're doing any type of out-of-band updates like the one that we just talked about, just include all the selection set. It makes your life a lot easier. But if you do want to troubleshoot a little bit, Amazon EventBridge targets do have the ability to have dead letter queues attached, which are really helpful for events that can't be delivered to the target. And AWS Appsync also has logging that you can turn on at varying different levels to help you troubleshoot. I am very familiar with those because I have to use them all the time to troubleshoot my code. All right, moving on to our next pattern. So we've been previously talking about AWS Appsync, which uses GraphQL. This pattern is what we're calling the no GraphQL events pattern. This is using a new feature within AWS Appsync called AWS Appsync Events, which is a true pub-sub model, no GraphQL required. Integrating this into our event bus architecture, our event processing architecture, our stream handler here is essentially doing an HTTP post operation to update our subscribers that are subscribed to the specific channel namespace that we are creating. So essentially what happens here, from a publish standpoint, publishers communicate with AWS Appsync events via an HTTP post operation. And then subscribers subscribe to that update using a WebSocket to get those updates in real time. So from the trade-off side here, this is really a true pub-sub model, right? We no longer have the GraphQL schema requirement. We have real power in how we segment out the messages and events that we're sending. We use channel namespaces, which we're going to talk a little bit about in more depth, but essentially just think of these as logical constructs to organize your events and your messages that are passing through your API. And again, no GraphQL schema required, which I still really do like GraphQL, but I know it is a burden for folks to kind of ramp up on that. So this is GraphQL free. On the trade-off side though, currently the subscription WebSocket is a one-way connection. So your subscribers can't communicate back over that WebSocket. They still need to publish via HTTP post. And then if you do need that catch-up API, you would need to implement that via a REST HTTP API or even just another true GraphQL API. From an authorization standpoint, again, this is still AWS Appsync under the hood, and we're leveraging a lot of the same infrastructure that we built to power GraphQL with Appsync. And so all the same authorization modes are still supported. And up until this point, all of the events patterns that we have talked through have this concept of data persistence, right? We're persisting the events in the event that we need to do an event catch-up later down the line, but not all patterns need that. And so we have a bonus pattern for you, which we're calling the fire and forget pattern. And essentially in this pattern, we send an update out, and whoever's currently connected at the time gets that update. And if you're not connected, you miss the update. That might work in some cases, might not work for all, so we're trying to balance out different use cases here. But in this one specifically, we'll talk about some of the key features of AWS Appsync events, which are still available in the previous pattern, but are more relevant for this one. So here, we're leveraging API destinations, which is a feature of Amazon EventBridge, to essentially connect and integrate to our HTTP post operation to do a publish over our Appsync event API. So that's step one. On a publish, we can actually invoke an optional event handler through Appsync events. And you can essentially think of this event handler as a bit of code written in JavaScript that does things like event enrichment or event filtering before that published event gets sent out to your connected subscribers. The same is true for connected subscribers. As subscribers establish that connection to your WebSocket API for the specific channel namespace, you can optionally invoke an onSubscribe handler, which can do things like granular authorization or enforcement of subscribing to only a specific channel within your channel namespace. And that's essentially what happens in this workflow. And those events get broadcasted out to any of your connected subscribed clients. talking about channel namespaces and the authorization controls of Appsync events in a little bit more depth, let's take this example. So we've been talking about flight status so far. So if we think about how we might organize our events for this flight scenario, we might define a namespace called flight status. This gets predefined, right? So we define this up front, and we define the configuration specifically for that namespace itself. We define multi-authorization modes, so what can people use to connect to this namespace for publish and subscribe. We can also add in those optional event handlers. And then for our specific channels, we might provide the flight ID as a channel, which gets dynamically created as you publish. So that RIV123 channel that's listed there doesn't have to be created up front and can be created as a result of something happening on the back end that you want to publish updates to and that you want your subscribers to receive information about. Similarly, we might have another namespace down at the bottom for seat assignments with a channel that includes the flight ID and potentially the user ID in addition. And what's unique about these different namespaces is we have completely different authorization configurations based on the needs of our publishers and subscribers. For our flight status flow, API destinations can either use an API key or it can also use OpenID Connect. And so we might have our publishers interfacing via API destinations using OpenID Connect authorization, but then our subscribers are display boards in the airport that need to get those flight status updates, or potentially user-based devices. So identity and access management authorization might fit best there. But for seat assignments, we might have a backend system that uses IAM to publish those updates out. And then from our subscriber side, we might want Amazon Cognito user pools because that's what our users are authenticated onto their applications with. So this gives you a lot of granularity in how you define both namespaces, the authorization for those namespaces, and any optional event handlers that you might need. So these are a few examples of what you might find within those event handlers that are defined at the namespace level. On the left-hand side, we have a sample for the onPublish handler. And here, essentially what we're doing is event enrichment. So for each event that comes through, which can either be one or a batch of up to 5, we essentially append some additional metadata onto those events. So taking that responsibility away from the client, the publisher, we put that into the event handler to add that additional metadata, like the time that it came in, what event we're at, as well as the session that we're a part of today. On the right-hand side, we're showing a sample on subscribe handler. And here, we're enforcing a little bit more granular authorization, right? We're saying that you can only subscribe to a channel that contains a group that you're a member of. And this can be really powerful if you need to get specific updates out to your users or members within a specific group and enforce that strong authorization control. From a broadcast and point-to-point standpoint, this is really just as simple as changing the channel that you publish out to, right? So you can, for point-to-point, you can provide a specific user-based channel or a unique identifier that they can subscribe to. And for broadcast, you essentially just broadcast out to a catch-all message that anybody can subscribe to. Again, here we're using the AWS Amplify API client, which by the looks of this, roughly 20 lines of code, this is pretty straightforward to implement. But you could also use your favorite WebSocket API library to establish that subscription. And from the post-publishing perspective, any HTTP client can also be used. All right, we've got one more pattern to talk through. And we're going to deviate away a little bit from GraphQL and our no GraphQL event pattern and talk about Mqtt with AWS IoT Core. If you're not familiar with Mqtt, it's another publish-subscribe messaging protocol typically used in IoT devices because it's lightweight and it supports a lot of the authorization modes that we typically see used in IoT devices. So the way that this integrates into our event processing workflow, our stream handler is receiving those events, it's doing its filtering, and it's actually publishing out to a specific IoT topic. Topics are very similar to what we talked about in the previous pattern with channels. They're just named a little bit differently and defined a little bit differently. But that's essentially what happens here. And then our subscribed clients just subscribe to the particular topic that they're interested in, and they get those updates. This flow is very, very flexible in the sense that you can create as many topics as you want. And broadcast and point-to-point is just as easy as the namespace example. You just define different topics for broadcast and for point-to-point workflows. Some of the trade-offs, though, in this approach are that it's actually only a single endpoint in your AWS account per region. So all the other patterns that we had talked about have their own endpoint depending on which API you're creating or however many APIs you're creating for your applications. But with IoT Core, you have a single endpoint per account per region. So could potentially be a little bit of a trade-off when you're designing for multiple applications. And then additionally, the authorization modes that we support in this approach are more focused towards IoT-based devices. So we support IAM, we support Cognito identities, but then we also support X509 certificates, which are commonly found in these IoT devices for authorization. And this is just an example of the implementation from the client perspective. I'll be honest, this is actually a lot harder to implement than it looks on screen. It was probably the hardest client implementation to do, but good news is, in our demo, we have example code that you can just take and run with if you go explore this pattern a little bit more. But for broadcast and point-to-point, like I mentioned, it really is just the difference between the topic that you define. And if there's a slide that you guys want to take a picture of, this would probably be it, because this is a snapshot of the patterns that we talked about so far. Really what this slide is meant to illustrate is that every one of the patterns that we've talked about today have their trade-offs, right? They have things that they're good at, they have things that you might have to implement yourself, but it really comes down to the use case that you are implementing, right? And so take this for what it is. You can use one or multiple of them in your application, but all the patterns that we talked about have their pros and cons. All right, and with that, I'm going to go ahead and switch over to a demo to kind of show you some of these things in action. But before I do, I'll kind of show you what we're actually going to talk through today. So we have a lightweight React application over here on the left that we'll show you. This is hooked into 6 of the patterns that we talked about. I'm including polling in there just to kind of highlight some of the trade-offs between the polling and the asynchronous real-time examples that we talked through. But we're simulating a bunch of flight status changes through a step functions workflow. Our step functions workflow is using the new JSON ADA capability that came out a few weeks ago. So you'll be able to leverage that in the source code at the end. And we're hooking into all of these patterns through the event bridge connection. So why don't we go ahead and see it? All right. So all of this data is already preloaded. Josh talked about this earlier. I mentioned it a couple times, but there's this idea of querying to get the latest. And then why don't we just go ahead and click start and fingers crossed that it all works. But let me talk you through what we're seeing here. So up at the top, we're actually showing what we call point-to-points. So we're subscribing specifically to one particular flight and getting that status. We're also implementing that seat assignments workflow with Appsync events and a different namespace to show you the integration between API destinations and Appsync events. And then as these updates start coming through, you'll start to see green highlights for the rows in our data that are changing, hopefully. It's always fun. Oh, there we go. It's always fun when you do a live demo. You never know if it's going to work. But you start to see that as things are changing, we have this additional field over here on the right, which is an event age. And this is essentially the time between when the event was created and the time our front end received that event. A couple things that you might notice already is that our direct to GraphQL pattern over there on the right middle, that one tends to be the fastest. And the reason for that is we have a lot less moving pieces between Event Bridge and our Appsync service that's publishing out the updates. For some of the other patterns, the updates generally come in within a few seconds when the events were created. But the one I want to call attention to is polling up there. And so polling, you'll start to see the event age varies anywhere from a few seconds all the way up to 15 seconds, which is our configured polling interval on the client side. And this really showcases where polling can be a little bit out of sync and introduce additional latency into your application. because you get updates only as fast as you're polling your backend. So we tend to have 8 seconds and 6 seconds and even 11 seconds for that most recent one. And I think that's it for the demo. So I'm going to go ahead and switch back over to the slides. And I will turn it back over to Josh to take us through the rest of our session.
All right, thank you, Kim. It's always living dangerously when you do a live demo because you don't know how the Wi-Fi is going to work in here. So thank you all for not being on your mobile devices at the same time. So next, we're going to talk about long-running processes. And again, these are things that generally take longer than 30 seconds or so to respond. So of course, we've been getting more questions about this and with the rise of generative AI, but I'm not going to talk about that. We're going to talk about a couple of other use cases. And kind of going back to earlier, this idea between polling versus subscriptions. So we can implement these long-running processes using any of the patterns that we've shown, right? Literally any one of them would work. But I personally prefer the subscription approach for this use case as well, because it gives you the ability to go for 10 seconds or 10 minutes if you really want to. There is some added technical complexity here. But again, these are pretty well understood architectural patterns, and you can boil them down to just a couple of components, as Kim showed, like just event bridge and Appsync events if you want to. So kind of taking the flight example a little further, we can do something with a flight search, right? And I implemented something like this a number of years ago with Appsync calling step functions directly. Doesn't matter so much. But here we might be searching a couple of different inventory providers, maybe for different flight awards that are available. And as each step of this workflow starts to come back, right, we're running all of the searches in parallel, we can actually publish the results individually. And then when all of the providers have responded, we can aggregate those results and publish an event to the front end that says, hey, this is the end of the list. So this type of scatter-gather approach works really well here as well. This is actually the second year in a row at reInvent that I've used this exact architecture diagram. And my talk last year had nothing to do with this. It was more about Appsync and some other topics. But I had about a half dozen people come up to me after the session to ask how to implement the little diagram that was on the right-hand side of the screen. So what's happening here, we're using Appsync, but again, lots of options, is we're going to have Appsync go start a query with Amazon Athena. Athena runs that query against some data in an S3 bucket, and when it's finished, it writes the results to a second S3 bucket. When that happens, S3 publishes an event. We can subscribe a Lambda function to that event. It could also go through Event Bridge if we wanted. And then our Lambda function says, OK, this query is finished. It goes back to Appsync, or again, any of the patterns we just talked about. And it lets the client know that the results are ready so that the client can maybe use like an S3 pre-signed URL to go download that result set. So again, this is actually pretty helpful depending on the types of work you do. And it was really interesting to a whole bunch of people last year. Last topic we're briefly going to talk about is push notifications. So functionally, push notifications feel a lot like those real-time updates. But there's third parties involved, and there's some different semantics as well to be aware of. And you also probably want to filter these things a little bit more heavily. If I'm getting a push notification every time my flight status changes, I'm probably going to turn those off. So in the demo code, we actually kind of limit the filter only to like delays or super important things. And that's really easy to go implement. So we still want to go implement these types of real-time updates, but we're going through some third parties in this case. So this is a quick example using web push. Yes, you can do push notifications to browsers on the desktop. There's a couple of prerequisites before we can even send our first push notification. First, the client needs to subscribe. And they do that, depending on the browser, they might need to click a UI element to get that subscription option. They do that by subscribing. That subscription is going to send some tokens and other information off to some server. In our case, it's a Lambda function that goes and writes that data into a subscriptions table. this is going to start to feel a lot like that two-way WebSocket pattern that Kim shared earlier, with some slight differences. Then when the user wants to subscribe to updates on a particular order or to flight status changes, we need to actually marry those two things together. We need to marry that order and that subscriber together in the subscribers table so that our event handler eventually is able to go look up and know which subscribers want to be informed of any updates. So as events come off of our event bus, the event handler is going to go check the subscriptions table, say who cares about this, and then it sends that a request to some notification service. Now this is Apple or Google or Firefox, and we don't really have control of that over the delivery anymore per se. And then those are going to go deliver the notification to the browser. And in this case, you also need something like a service worker to actually go receive those responses, but that's those messages. It's a little outside the scope of what we're going to talk about today. But we do show how to do this in an older version of the demo code that you'll get in just a few minutes. You can go take a look at that as well. For mobile, things are a little bit simpler because we can use a service like AWS end user messaging to take care of a lot of that subscription stuff. Right? End user messaging will store the device token if we want to, but we do need to kind of marry up still which subscribers are interested in which types of events. So in this case, we're subscribing through end user messaging. As the events come off the bus, we have a notification handler that goes and inspects them, figures out what update to send to which subscribers, and then again uses end user messaging to do that. But end user messaging does go through some notification service, Apple or Google, to actually publish them out with best effort to your mobile device. So again, the semantics are similar. What we're trying to achieve is similar, so we didn't really want to belabor this section, but there's some other thoughts, there's some other things involved, and some other services in particular. So that's the bulk of what we've got for you today. So we've talked through real-time events, 6 or 7 different patterns to implement those, how to implement long-running processes, and then also how to implement push events, and how you can use those same 6 or 7 patterns across all of these interactions. So you can find all of the sample code on GitHub, with the QR code and the short link are still working. So either one will get you there. Pausing for one more second as people still have phones up. As you wander around reInvent this week, a couple of other sessions you might want to check out. So we have one on building event-driven architectures, which is fantastic. We also have a very popular chalk talk if you're trying to figure out should I use API Gateway or Appsync or ALBs. And then just plugging myself, I'm doing another talk later this week on security if you're interested. And with that, thank you for spending the hour with us. Please do take a minute to fill out the session survey. We love 5s, but we really do appreciate your feedback so that we know how to make this session better in the future. Thanks so much and enjoy the rest of your week.